Hello everyone, welcome to Learn. I'm here with Albert today and we'll keep going with our discussion on nuclear energy. So for today, we're going to talk about nuclear fusion. Though it is still part of our nuclear energy topic, it is actually quite different from nuclear fission. So let's start with the basics. Nuclear fusion, simply put, is a reaction in which two or more atomic nuclei are combined to form one or more different atomic nuclei, but they're heavier, and subatomic particles such as neutrons or protons. And apparently, because of what we've mentioned before, there would be a mass difference or mass defect between the reactants and the product. And this mass difference is going to be manifested as either the release or the absorption of energy. And for our purpose, we're going to talk about nuclear fusion and gaining energy. We'll only talk about the case in which nuclear fusion emits or releases energy. So do you remember this equation over here? It basically tells us that when you add several protons or neutrons together into a nucleus or two smaller nuclei, their mass will be actually less than the protons and neutrons simply by themselves. And this lost mass, or delta M, will be released in the form of energy, either by heat, radiation, or sometimes kinetic energy. And this delta M times c squared actually has its own name. It's called binding energy. Binding energy is, well, quite straightforward, and from its name, you probably can tell that it basically is the energy required to bind small nuclei to a heavier nucleus. And actually, it can also be the energy released when you bind the small nuclei together. So, just like nuclear fission's process, nuclear fusion is also an exothermic process, meaning it releases energy. So, we will use it to our advantage and get some, well, I guess, free energy. Well, now you might want to ask, then how do we do nuclear fusion and how do we use it to get energy for ourselves? Well, just like nuclear fission, we have nuclear fusion reactors. However, we don't really have a great reactor that is good enough to make our scientists happy, so yeah, they're still working on it. So for now, I can introduce to you two of the most promising possibilities of future fusion reactors. So these two possibilities are magnetic confinement fusion reactors and inertial confinement fusion reactors. So let's start with magnetic confinement fusion then. Well, to put it simply, it is basically an approach to generate thermonuclear fusion power that uses magnetic fields to confine fusion materials such as, well, hydrogen in the form of a plasma. And this plasma is going to be, well, really hot, will be confined in a tokamak, something that looks like this. Well, by having these fusion materials running with each other inside a magnetic field in the tokamak, well, those magnetic confinement fusion reactors is capable of combining light atomic nuclei such as hydrogen and form heavier ones such as helium and therefore producing energy. So one of the most famous magnetic confinement fusion reactors these days is the International Thermonuclear Experimental Reactor, or short as ITER. It currently is the largest experimental tokamak nuclear fusion reactor, and it has 10 times the plasma volume of any other tokamak operating today. It was not until a long time ago that ITER reached the benchmark of output greater than input, in which the ITER can actually produce an output of 500 megawatt with an input power of only 370 megawatt. This is actually really remarkable since we're using the concept of nuclear fusion to actually generate energy for ourselves. But sadly, we haven't found a way to use these energies or to convert them into, well, electricity that we can use for every day. But that is a topic for another day and still one of the greatest technical difficulties for scientists today. Okay, now let's take a look at inertial confinement fusion reactors then. Well, unlike magnetic confinement fusion reactors, these inertial confinement fusion reactors initiate nuclear fusion by compressing and heating targets filled with thermonuclear fuel. Well, these thermonuclear fuel are typically a pellet containing a mixture of deuterium-2H and tritium-3H, which are all isotopes of hydrogen, while making them just a few more, well, neutrons than a normal hydrogen. In order to compress and heat up the fuel, some amount of energy must be transferred to the target on the very outer layer of it using things like high energy beams of photons, electrons, or ions. although almost all ICF devices as of 2020 use lasers. Those beams, after heating up the outer layer, will explode outward and creating a reaction force against the target and therefore making it accelerating inwards and compressing the fuel. This kind of creates some shock waves that could travel inward through the target, and some of those sufficiently powerful waves is capable of compressing and heating up the fuel at the center and creating fusion and making energy for us, by the way. One of the examples of inertial confinement fusion reactors is the National Ignition Facility, or NIF. Although construction on the NIF began in 1997, but some management problems and technical delays slowed the progress into the early 2000s. Still, in 2021, after many years of research and fuel target design, NIF was capable of producing 70% of the energy of the laser, meaning NIF's output is currently 70% of its input. This is still quite a remarkable achievement since it has beat the record set in 1997 by the jet reactor at 67%, and it also tells us that NIF is still growing and is capable of producing some more amount of output in the future. Well, looking back, we have made a lot of progress, but still, we have a long way to go in perfecting nuclear fusion. For example, how do we even find a material for the inner walls of the magnetic confinement fusion reactors that is capable of sustaining fusion processes for a long time? Or how do we transform the power created in the fusion processes into something we can use, such as electricity? Well, that'll be something time will tell us. But before that, it is perfectly fine for us to imagine a world with perfect nuclear fusion reactors. And that is the content for our next video. See you next time, and thank you for coming to Turtle Learn.